Hi, my name is Manish Gupta, and in this video, I'm going to talk about how do you steal part of a production language model. So I never thought I would talk about stealing, but well, here is an interesting work on how people can actually steal a part of a production language model, where the only thing that is available is an API to access the model. Right? So essentially, let's start by first discussing what part of a language model can you steal and how. Right? Um, or rather, the main question is how much information can an adversary learn about a language model by making queries to its API? So of course, the model is not available. The weights are not available to you. Only API access is available. And you want to basically get some part of the model. How do you do that, right? Now, of course, the work that I'm going to talk about is not as awesome as stealing the entire model. Well, I mean, it's an exaggeration. What this work really talks about is how can you sort of figure out what was the hidden dimension before the model projects that hidden dimension to the final vocabulary size, right? So if there is a large language model, which is basically trying to come up with the predictions, tokens, and so on, right? So what is the hidden dimension from which on which basically the weights W are applied so as to essentially get a vocabulary sized logit vector, which is basically used for final token prediction. Okay. So there are two things that you can predict using the work that I'm going to talk about in this video. One is dimension h, the hidden dimension h, and the weight vector or the embedding matrix in that sense is output embedding matrix in that sense. Okay. So this is important to know. I mean, although, it's not like you will get to know the entire model, but just these last layer and the hidden dimension is still important to know because that tells you about the width of the transformer model. And oftentimes that correlates nicely with the overall model parameter count. So for closed source models like OpenAI's models, recent models, you could basically try to guess what could be the model parameter count based on the width of the transformer model. It can also make more attacks easier. I mean, of course, this paper sort of talks about a few adversarial attacks, but there could be more attacks which can be based on this. So now what kind of APIs are we talking about? So OpenAI APIs, for example, they expose log probabilities. So essentially they don't just predict the next few tokens, but for the next few tokens, you can also ask what was the log probability of the generation of that token, right? So one, they expose log probabilities. So that's the first part. And then the second thing is that they can actually accept something called the logit bias. Now, what does that mean? So logit bias basically means that you can influence the probability with which a certain token is generated at the output. So in fact, you can influence the logit bias for up to 300 tokens on OpenAI's APIs, where the logit bias can be a number between -100 to 100. So if you set for a particular token, basically you provide logit bias as a dictionary, tokens and their bias values. So if you basically set the bias to -100 for a token, you are basically telling the model to block a token from being generated. And if you basically set the logit bias to 100 to a very large value, you're basically telling the model to generate the token more frequently or more with a higher probability. Okay. So for example, you're asking the model to create a recipe, right? And you don't have a pot to make that recipe. So basically, and you want therefore the model to generate a recipe without a pot. In that case, what you could do is to basically take the word pot, take its word ID, or rather the token ID, and then pass on bias as -100 to OpenAI's model so that it basically does not generate any recipe with a pot involved, right? Maybe you can generate a recipe with a pan involved and so on. Okay. But let's say you have a microwave and you basically want to have recipes using microwave being generated. So you could basically take the the token ID for microwave and then give a bias of 5 or 100 or whatever you want to have a positive value, basically trying to sample that token with higher probability in the output. Okay. So there are good use cases why APIs support logit bias as an input, and they basically give you full log probabilities. So that's that. And those can be used for adversarially attacking the model and stealing the last layer and the hidden dimension from it. Okay. In fact, this paper basically shows that you can extract the embedding layer of this last layer of several OpenAI models with a mean squared error of 10 raised to -4, as low mean squared error as that, right? Um, um, so for the rest of this video, let's assume that the vocabulary has size L, which is and expressed as a set X, right? X is the vocabulary and it has a size L. And this is how basically the last layer is functioning. So essentially, You have the input prompt P, which is basically being encoded by G theta encoder. So essentially with the parameters theta, such that G theta P is basically of size H, this dimension H. And then the matrix W actually projects it into the vocabulary space on which you can apply softmax and essentially get the final probability values. Okay. So of course, you do not have any access to this G theta because that's a hidden model. Of course, you also do not have access to W via the API. All you have access to the model. All you have access to is this API O, which basically takes in a takes in a prompt P and gives you the token Y. Well, it can also tell you the logits associated, with the predicted output. So now APIs differ in different from this perspective. So some APIs can actually give you all logits. So basically, if the vocabulary size is L, well, they'll give you the probability values associated with all of those, tokens. Okay. Some of them give you only for top log. They only give you top log probabilities. So what does that mean? Basically, maybe they will give you top 5 predictions for the next token, and each of them is associated with a log probability score. And some of them basically just give you the next 5 tokens or the 5 possibilities for the next token, but they don't really give you any log probabilities. And in this video, I'll talk about how all of these cases basically can be attacked. In all of these cases, you can actually do this attack and get the dimension H and the weight W. Okay. So let's talk about the simplest case. Okay. So how can you extract hidden dimensionality and the full projection matrix? Basically, remember hidden dimensionality is D and projection matrix is W. You can also call this projection matrix as the embedding matrix. So hidden dimension D and projection matrix W for logit vector APIs. What are logit vector APIs? They're APIs which basically give you access to the full full output logits. Okay. So recall that this is what the API does. It basically takes an input prompt P and then applies the G theta encoder so as to get an output of dimensionality D, multiplies by W projection matrix and gives you the output logits. So essentially it gives you the entire set of logits. Okay. So now the idea is that how do you really predict D and W based on this? Okay. So the idea is super simple. So the idea is to essentially fire a whole bunch of queries to this API. Okay. So in fact, I'll go over this algorithm, and that's basically as simple as how you can actually extract D and W for this particular API, which returns all the logits. Okay. So you essentially have an LLM-O, which basically returns logits. Okay. So what you do is to basically fire n queries. Okay. So you're basically going to prompt the LLM with n different queries, and this n value has to be greater than h. So of course, what you want is sorry, the dimensionality was not D, it was H. Sorry, it was H, right? So you want to basically get the dimensionality H. So you basically fire how many queries? Well, queries n much larger than H. So ideally n should be much larger than H. Okay. So, and then you initialize an empty matrix Q, which basically has this length n into L. Now, what is L? L is the vocabulary size. Remember, what is L? L is the vocabulary size. So what is Q? Q is basically Q is basically of the size n into L. So for every query, you are going to get a L-sized vector, and you're going to populate it in Q. Okay. So that's what you do in these steps, steps 3 to 6. For each of those queries 1 to n, you're essentially going to fire that to the LLM, or rather, basically you take that prefix or the query and you fire to the LLM so as to get the logit vector Qi. Okay. So overall, that gives you n rows in this matrix Q. And then what you do is to essentially do singular value analysis or the eigenvector analysis, right? So you basically try to figure out the eigenvalues of this matrix Q. So lambda 1, lambda 2, up to lambda n, and so on. Okay. So what you would observe is that at a particular threshold, these eigenvalues suddenly drop. So for example, if you sort these singular eigenvalues and look at their magnitude, so you see the magnitude, the values, right? And let's say you were doing 3072 queries. You did those 3072 queries. We are looking at this purple curve. What you would observe is that suddenly, at some point, the eigenvalue difference between these consecutive eigenvalues is super high, super large. Okay. That is the point which you can basically say is the dimensionality of this model. So as you can see, the dimensionality of this model is 2048. And actually, it's predicted rightly so because this experiment was done for Pythia 1.4 billion model, where the hidden dimensionality is 2048 actually. Okay. So of course, the larger the number of queries that you run, the starker this difference between 2048 and 2049th eigenvalue in this case. So as you see, I mean, in the red curve also there's a gap between the 2048 and 2049th value, but it's sort of rather smaller. Okay. Of course, if you basically fire queries less than 2048, then you won't see that gap. So therefore, you must choose an n which is larger than h. Okay. So then what do? You basically do the eigenvector analysis, and you get the eigenvalues, sort them by their sizes, by their magnitudes, and then you basically figure out that particular that particular point where there's the largest multiplicative gap between consecutive singular values or eigenvalues. Okay, that basically decides your h or the hidden dimensionality. Okay. You can also see this ratio being plotted here, this multiplicative gap. So this ratio of lambda I to lambda I plus 1 being plotted in this plot. And as you can observe, at 2048, this value is super high. Right? So that's that. Now, so that was about the hidden dimensionality. But how do you get the full projection matrix? Well, to get the full projection matrix, you take this matrix Q that you had obtained here of logits returned by various queries. You do SVD decomposition for that. You get U sigma V transpose. And there is some theory which basically shows that U sigma is essentially the weight matrix that you're looking for multiplied by some matrix G, which is a H cross H small matrix. Okay. So if you basically look at U and sigma, of course, you're doing some truncated SVD here. So or rather, you're doing the SVD here. But if you basically multiply U and sigma, that is more or less equivalent to W with this little G transformation applied, which is basically a linear matrix transformation, H cross H matrix. So you don't really exactly get the W matrix while doing this attack, but you basically get a simple linear transformation of the W matrix while doing this attack. Now, how good is this linear transformation, right? So therefore, what they do is to basically take the actual W and they try to essentially, approximate this or rather estimate this matrix G, right? So they take the actual W, and remember, if the estimated W is used, if the estimated U into sigma is WG, so what they try to do is to basically take the actual W. This is the actual W, and they take the U sigma that was computed using the SVD decomposition multiplied with G, and they try to estimate G such that the difference between these two guys is minimized. Root mean square error is minimized, right? And then they basically report the mean squared error. So what do you see here? You basically see that for a lot of models, it is nicely estimating the hidden dimensions, right? So it is nicely estimated. So this is the real hidden dimension. So this is the real hidden dimension. This is the stolen hidden dimension or estimated hidden dimension. And as you can see, it's basically doing a great job, except for this small thing where it's screwed up slightly. But otherwise, it's doing a great job at figuring out the hidden dimensions. And the RMSE values are so small. So essentially, it's able to predict those weights also very accurately. Okay. Okay. So now let's look at a more complicated setting where you don't really have the access to full logits, but you only have access to the top 5 logits. Okay, so you basically have access only to the top 5 log probabilities. So what do? Okay, so essentially the situation looks like this. You essentially pass in a prefix p. So essentially you're calling the API like this, O of pp. So what is p? P is the prompt that you pass on. And then B is the logit bias. So essentially, you can pass on various logit bias values, a dictionary where you can actually say, hey, here is the token, and this must be a logit bias for it. Okay. So basically, of course, it applies log softmax and then takes the top k and returns, right? That's what the API does. Which basically means log softmax effectively means that it's basically doing the actual value minus log of summation over all other i's, right? All other i's except for the top guy. Okay, so that's what it is actually doing, and this is no big deal. This is basically what the typical last layer of a LLM does, right? And it's basically returning the top k being 5 here in our case because we're talking about 5. Okay, and the question to ask is, can we uncover the full logit vector based on just these 5 values, right? So remember, if we can uncover the full logit vector, then we just go back to the previous slide and apply the same methods. But to get the full logit vector, how do we get this full logit vector based on just these 5 values is the question to ask, right? And we don't just want to get the full vector, but we actually also want to minimize the token cost and attack duration. So basically, you don't want to call the LLM too many times so as to basically get this. And you also want to do this in limited amount of time, given API rate limits. They will throttle you and so on, right? So, so the idea, the basic intuition to do this is as follows. You can actually recover the complete logit vector for a prompt P, for input prompt P, by cycling through different choices for the logit bias and measuring the top k logits each time. Okay. So the point is that typically, if you basically just gave the prompt P, you would just get the top 5. Now you want to get the others also. I mean, the vocabulary is large, maybe like 100,000, right? So how do you basically get the others also? Now, of course, the vocabulary is typically known to people. So when you want to essentially get all the other tokens as well, you have to ensure that they become top 5. Okay, because that is how you will get the logit values, right? Now, to ensure that they become top 5, what you must do is to basically cycle through the entire vocabulary and choose which 5 you want to get the logits for. And for them, basically set the bias value to a very high value B. Okay, it could be like 100, 200, whatever, so as to ensure that it's that those are the 5 tokens which are going to be selected by the LLM to output, and will output the logit values anyway. Okay. Now, of course, you must repeat it for each of those sets of 5 in the entire vocabulary. Mod of X being the overall vocabulary size, so that you essentially finally end up getting the entire logit vector. Okay. So now, so effectively what you're doing here is basically you're querying the LLM, mod of X divided by 5 times, so as to get the entire logit vector. Each query is going to promote 5 tokens, k to k plus 4 into the top 5. Okay. But unfortunately, there's one problem. And the problem is that APIs do not return logits. So they are not going to return these top 5 logits, unfortunately. They return log probabilities. Okay. So they return log probabilities. They actually do not return logits. Okay. Now that causes a challenge, because if you really look at it, right, if you basically talk about log probabilities, which is what is actually mentioned in this formula, right? If you really look at log probabilities, if Zi are the original logits, it's basically going to apply the bias B, the logit bias B that you said. And then it's basically going to apply this subtraction part, right? Which basically runs over all the tokens other than I. Okay. So that's that. So therefore, unfortunately, by just looking at the predicted logits or the predicted scores that the API returns and subtracting B, you can't basically get the actual logit value, unfortunately. Okay. So therefore, you need to do something to handle this term here. Okay. And the way to handle that is to basically have some sort of a common reference via which this term can get cancelled off in some ways. Okay. So the idea is that let's basically take the top token for a prompt, and let's say that the top token is R. Okay. So if you basically give a prompt, the LLM will have a highest probability of generating some token, right? So let's call it R. Now you want to learn the relative difference between logits of any random token I and the token R. Okay. So remember, R is not a random token. It's basically the token which the LLM would predict naturally with the highest probability without any logit bias. Okay. So what you want to do is to learn the relative difference between the logits of token I and R. And you want to compare the reference token. And the way you do this is as follows. You compare the reference token R to 4 other tokens per query. Now remember, you can only pass 5 tokens in the query, or rather you can only get logits for 5 different tokens as output. And therefore, you're basically going to say that, hey, I'm going to pass R without any bias, but I am going to pass these 4 tokens with a bias of capital B, which means that, R is going to come at the output anyway, because it's the most probable token naturally. But these other 4 tokens will also come at the output because you have artificially boosted their bias values and therefore their probability values. Okay. Now let's take a token I, which is one of these 4, right? So essentially for that one, now what you could write is this. Now, it requires a little bit of math to sort of understand that this is possible. So what you're going to say is that this Y is basically the logit that you obtain from the API, right? So the logit for R minus logit for I, or the score for I from the API minus the bias, which you know because you passed that, right, is equal to ZR minus ZI. Now, of course, ZR and ZI are unknown because they are the original logit values, right? You basically, of course, want to find them. So they are unknown in that sense. Okay. So that's basically going to be ZR minus ZI. Okay. Now, since ZR is unknown and it's a reference token, let's just set ZR to 0. Okay, so basically all the logit values that you will obtain are going to be therefore relative to ZR, relative to a particular value, relative to a particular token, the top token in that sense. And that's okay. I mean, getting things relative, getting the logit scores which are relative to a particular token is okay, because finally you're going to do eigenvalue analysis, and eigenvalue analysis is going to be I mean, just a multiplicative factor in that sense. So therefore it's okay, right? So you fix ZR to 0 and therefore derive what is ZI. So in one query, like earlier you were doing five tokens. Now you could actually handle 4 tokens because you need 1 for the reference anyway. You'll have to repeat R in every query that you do. Okay. So that's that. So overall, the query cost for this is going to be 1 over k minus 1 queries per logit. So for getting one logit value, you basically need to run this 1 over k minus 1 times, where k is 5 in this particular case, right? And remember, the attack requires you to run how many queries? Well, n different queries. So essentially, overall, you will need to run it several times. How many times? N into x divided by k minus 1 times, where x is the vocabulary size in that sense. Okay. Now, what happens if basically the API just allows you to have just one top one log probability score, and that too, it allows you binary logits only. Okay, so the API has 2 constraints now. It doesn't give you full logits. It basically only gives you top one logit, a top one log probability score. And second, constraint is that each logit bias is only -1 or 0, not between -1 and 0, only -1 or 0. That's the only thing that is allowed by the API. Okay. So now, of course, this is a difficult case. It's difficult to learn any information about a token if it is not going to be, the most likely token. So just like in the previous case, your job is to be able to push the token for which you want to know the logit to be the top one, because unless it is top one, you won't be able to figure out how to use the logit, that is how to use the score predicted and sent to you by the API. Okay. However, of course, the goal is basically you will query the model twice, one without any logit bias and one with the logit bias of -1 for the token T, thereby pushing the top token to be to be the one pushing the particular token to be the top token in that sense. Okay. So, and then you can actually repeat the same process as on the previous slide. However, you will take many more queries to be able to reach a good estimate of the dimensionality and the weight matrix. Okay. Now, further in this paper, they also talk about how can you try to essentially do the same things from a log probability free attack perspective. So now the constraint on the API is that it doesn't give you any log probability scores. It just tells you what is the highest probability token, but doesn't give you log probability scores. And also, but on the other hand, it allows you logit bias. Okay, this time it's not a binary logit bias. It actually allows you various values of logit bias, but it does not give you the log probability scores. So even for that API, it turns out you can actually break the, you can actually figure out the dimensionality, hidden dimensionality, and also the weight matrix. The way to do this is to do binary search to increase and decrease the logits. So you can supply several logits. You can try to increase and decrease the logit scores for different tokens, until increasing any token by any particular logit score for that token, logit bias score for that token, until increasing or decreasing in the logit bias score for that token by epsilon will make it the most likely. Okay, so you basically do a binary search. You try to actually continuously keep increasing for every token, right? Not all at the same time, but for every token, you basically try to increase the logit bias a logit bias score for the token by epsilon until essentially in a binary search manner, until essentially you figure out that point where increasing it is not going to where increasing or decreasing it, it's basically going to change whether it is being returned as the topmost token or not. Okay. Performing this, of course, doing this, and there are more details in the paper how this will help you get the hidden dimensionality and the weight matrix. But performing this binary search is not going to be very effective. I mean, of course, it's not going to be very efficient. It's effective. You can basically get the weight matrix in the hidden dimension, but it's not very efficient. So therefore, they essentially provide further methods to actually make it more efficient. One of those methods is to basically try to predict multiple tokens rather than just one token in the output. Then that's how you can actually do them in parallel. One call gives you multiple top tokens, and you can try to do binary search with multiple tokens together. Okay. Okay, so that was that. Now, how successful were they in basically stealing the models in that sense, right? So they experimented with several OpenAI models, and they worked in collaboration with OpenAI for this particular work. Of course, they told OpenAI that we are trying to steal your models in that senses, and essentially did that. So they were able to rightly guess for the ADA, Babbage 2 models that this is the hidden dimension size. They were also able to figure out the hidden dimension size for GPT 3.5 Turbo and Turbo Instruct and so on, right? But did not publish it because OpenAI restricted them from publishing these numbers, although OpenAI confirmed that these numbers were actually correct. Okay. They had to use several queries so as to be able to get these values, hidden dimensionality values. But overall, even for the largest models like 3.5 Turbo 1106, they required about $800 of worth of LLM calls to be made to figure out this. Okay. They were also able to gather the weight metrics, and for that they were able to, so these are estimates. They did not really get the weight matrices for these large models, but for smaller models, they were able to get the weight matrices with a reasonably small root mean squared error in very small dollar amounts. They are estimating that they would require about $8,000 so as to essentially get the weight metrics for this model. Of course, you can't do that anymore because OpenAI, after this work, stopped giving out log probabilities, and that is why you might basically, can't essentially get the weight metrics that easily now. So that's that. So this table basically shows you what is the accuracy with which they were able to obtain the weight matrix, right? So these are various methods that I talked about. So the first one was log probability 4 method. So remember, you have the top 5 logits, and essentially you can basically get the value for 4 of those logits at a time. So that's the log probability 4 method. We also talked about the log probability 1 method right here, log probability 1 method. They also have in the paper log probability 5 method and methods without any log probabilities. Okay. So these ones basically don't use any log probabilities. These ones use top 5 log probabilities. The weights that they were able to obtain in the weight matrix, they were able to obtain correct weights up to 23 bits of precision. Now that's basically beautiful because typically with quantized models, you don't really require 23 bits of precision anyway. So in some ways, they were able to get the weight matrix almost as is when you really think about this log probability for kind of a method. I mean, essentially, if the API was exposing 5 different log probabilities, you could actually have the embedding metrics right with you, with these kinds of attacks. With a cost of about 0.25 queries per logit. So of course, if the vocabulary size is larger, you need to do more queries, which will cost more LLM dollars. Right? Now, essentially, as you see, if log probabilities are not made available, then it is very difficult to get good precision, and it is expensive as well. You require like 10 queries per logit, which is much more expensive, right? But they do have a method which basically can give you like 18 bits of precision with about 4 queries per logit. So it's expensive, but it is possible to get the weight matrix with pretty good precision. So how do you defend against such attacks? Now, of course, you could basically, OpenAI kind of API providers, how can you defend against such attacks, right? One way is to remove logit bias completely, but logit bias is required. I mean, logit bias is a great feature to have where you can actually, let the clients decide which tokens should be generated versus not. Okay. So in that case, you could basically simply have clients basically replace logit bias with a block list. So the clients could say that this is a block list or this is an accept list, right? The exact value of the boost that is provided via the logit bias can actually be hidden from the clients. You could also make architectural changes. So rather than having one last layer, embedding layer, you could actually divide into 2 layers, which basically means W can be split into A transpose B, where basically, with the non-linearity in between, much like what LoRa does in that sense, right? So that's one way of not disclosing the hidden dimension at all. Okay. And not giving away the full hidden matrix, the full embedding matrix. You can basically that way the attackers will only have access to B but not to A. Right? You could also make post hoc architectural changes. So, for example, you could fool the attacker by expanding the dimensionality of W and concatenate extra weight vectors, which are not really learned but just added artificially after the training is done. So they do not impact the predictions, but have non-trivial singular values just to fool the attacker in that sense. Other ways of mitigating such attacks is basically do not have an API which does not support logit bias and log probabilities together. If you are basically in one query, if you're basically accepting log probabilities, then don't return log probabilities. Or if you're returning log probabilities, then don't accept logit biases, right? So either accept logit bias or output log probabilities. Prohibit the queries which basically require both. They basically want to give you logit bias and also take log probabilities. Prohibit those queries. Okay. You could also add noise to the output logits of any given query. So that disables the guys from doing their job nicely, right? From figuring out the weight metrics and so on. Rate limit on the logit bias. So essentially, if you basically are accepting queries which have a logic bias in them, rate limit them severely or detect such malicious queries and just block attackers by their IPs and so on. Okay. So that's it for this video. In this video, in summary, I talked about model stealing. So, well, it's not literally that you get the full model. You basically can get the hidden dimensionality and the last layer weights up to a certain approximation, in the sense that you don't really get the full weight matrix also. You get a weight matrix which if multiplied by multiplied by some small h cross h matrix G is approximately equivalent to the actual weight matrix, right? So essentially, so you get W hat, right? So basically, which is not exactly W, but that's that. I mean, but that's still useful for various purposes, right? So APIs differ in terms of whether they basically give you all logit probabilities or all logits or log probabilities or top few log probabilities and so on. The more they give you, the easier they are to attack. Logit bias is a way of sort of fiddling around with the last layer, and therefore, logit bias basically makes it easier for the model to be attacked. Okay. Okay, that's it for this video. Hope you liked the video. Thank you for watching. Connect me on my LinkedIn or look at my search on my homepage.